Okay, so I didn't actually get the memo for the snappy title, so I apologize for the academic language used there. So what do these three images have in common? So the first image is shows a series of neuroimages generated to understand the causes of schizophrenia. The second is a simulated collision of two protons thought to show the signature of the Higgs boson particle. And the third is a simulation of the tropical storm that hit Haiti in 2010. The common link? Well, to create all of these three images involves computing millions of calculations, resulting in the generation of huge amounts of data. For example, the Hadron Collider, source of the second image, generates more than a gig of data per second. Now that's 6 times the contents of Encyclopedia Britannica per second. Manipulation of data on such a huge scale requires powerful computer processing facilities. Thankfully, we do have the high-performance computing systems available, enabling us to speed up the development of new drugs and enhance our learning of dark matter and predict the impact of floods. So I'm going to show you a demo here. As we don't have tropical storms in Ireland, I'm going to show you a demo of a flood in Limerick City. So the structure to the back there is of a supercomputer, and each compute node contains a number of processing units. So when the simulation is run, the cells containing data about things like soil viscosity, land topology, etc., are distributed across the nodes in the supercomputer. Calculations then are run in parallel, like Michael described in his presentation. When the parallel processing is finished, the data returns. And you can see now the flooded images on the cells that are coming back. So the end result is a flood map of the region. Now, this was a simulation for Limerick City. Imagine running such a simulation for an entire country. On a single processor desktop machine, this could take years, but when run in parallel in an environment like that, it's reduced down to days. Now, dividing up the data or data decomposition introduces a lot of complexities. So cells need to know where they are on the grid, what data they have, who their neighbours are, what they need to communicate, etc. So the sketches shown here in the bubble were gathered from parallel programmers and show the methods that they use to perform data decomposition when running a flooding simulation. As you can see, pen and paper, it's completely manual. There is no tool support available in order to carry out this. To this end, my research involves the creation of data-oriented abstractions in order to help parallel programmers to distribute and manage their data. You can see here a visualization of how this data will be presented. So the end result is to make the parallel process more efficient and less error-prone. After all, we need science, be it in the medical, physics, environmental domain, to continue making breakthroughs. Thank you.